Hello everyone, I'm Zhepeng from Department of Computer Science at Hong Kong Baptist University. Very glad to introduce our recent work on how to realize privacy-preserving contact tracing to combat pandemics based on blockchain. In this talk, I will first introduce some background about contact tracing and the challenges we meet. Then I will present our P2B trace system. Finally, I will present some evaluation results and potential research directions. As a non-pharmaceutical intervention measure, contact tracing has shown its effectiveness on pandemic control. With such a system, we can timely identify the people who had contact with infected persons. So, the identified close contacts could be provided with early quarantine, diagnosis, and treatment to track and break the transmission chain of the virus. This image here shows an example of the virus transmission. A recent study published in Science has shown that the COVID-19 pandemic can be stopped if around 60% of the close contacts can be identified immediately, especially combined with some other preventive measures. Traditional manual contact tracing is not efficient because it is limited by a person's ability to recall all the close contacts and the time it takes to reach all these contacts. Usually, it is also very hard to trace all contacts in public venues if people do not know each other. This method is intensive on human labor. This image shows the manual tracing in the real-world scenario. So, in a world coexisting with the virus, an effectiveness and a secure digital contact tracing system is much desired. There are several challenges in building an effective digital contact tracing system. First, user privacy protection during data collection and processing has a significant impact on the uptake of the system. So, protecting user privacy should be the first requirement. Most existing systems are designed with a centralized model. Users upload their personal data to a central server for contact matching. However, user privacy could be compromised and the server becomes a valuable target for attacks. Second, verifying data integrity is crucial to ensure the correct contact matching and proximate claim. This challenge is twofold. One is how to prevent confirmed patients from modifying their historical contact records to generate false matching. The other one is how to prevent unconfirmed clients from tampering with matching results to generate false exposure claim. In existing decentralized systems, data will be collected and stored on the user's local devices. However, the integrity of the user's local contact data cannot be guaranteed. So, to meet these challenges, we propose P2B Trace, a blockchain-based contact tracing system, which ensures data integrity and user privacy. This system enables users to confidentially conduct contact matching on local devices based on historical contact records, where a trusted server is unnecessary. This figure shows the P2B trace system architecture. Our decentralized system mainly consists of 4 actors. The patient is a virus-infected person, and the client refers to an unconfirmed person. The workers are responsible for appending new blocks to the blockchain. The authority represents a component in the healthcare system to provide a close proximate certification for further screening. The system mainly includes 3 modules. First, in data generation, compatible with most decentralized contact tracing systems, P2B Trace also uses Bluetooth to generate and exchange anonymous identifiers with smartphones. Users update their identifiers at regular intervals and constantly record encountered identifiers nearby. As such, each user will build a generation list (LG) and an encounter list (LE) at a specific frequency, for example, every day. Moreover, to enable verifiable contact tracing, an authenticated data structure (ADS) is constructed for each LG and LE and stored on the blockchain. Second, once confirmed, the patient will upload historical generation lists to the blockchain. Observing the patient's contact records, all clients will conduct a cross-check with respective encounter lists on local mobile devices. If a match is found, the client can report this case to the authority for further follow-up. Third, to ensure data integrity in the tracing procedure, the verification will be conducted in two aspects. In the integrity of the patient's contact records is verified with the on-chain ADS, such as no fraudulent data are reported. Then, to prevent false proximity claims and protect user privacy, the client will generate a zero-knowledge proof for the authority, such that the contact matching can be verified without privacy exposure. Three security threats are considered in this paper. First, the patient is not fully trusted and may upload falsified and or incomplete contact records when confirmed with the pandemic. Second, the client is not fully trusted and may tamper with matching results to generate false exposure claim. And the third one, the authority is curious and may attempt to obtain some knowledge from the received data. To address the first threat, we adopt verifiable contact report to ensure the integrity of the patient's contact records. To address the second and the third threats, we propose privacy-preserving verifiable proximity detection that enables the client to prove the correctness of the matching results without revealing privacy. We define three levels of security requirements, include generation inclusiveness, encounter inclusiveness, and zero-knowledge confidentiality. The verification for the tracing procedure is built upon a blockchain-based hybrid storage model. The contact records and ADS will be stored on local devices. The ADS will also be stored on blockchain as notarization of the original contact records. We use Merkle hash tree to derive a Merkle root as the ADS to support the data integrity verification. The benefits obtained from the blockchain are twofold. First, the blockchain is maintained by untrusted peers in P2P network, so this can keep the decentralized architecture of our system. Third, the on-chain ADS is immutable, which can be used to verify the integrity of the patient's uploaded contact records and the client's claimed proximity. During the tracing procedure, once confirmed with the pandemic, the patient needs to upload his historical generation lists, LG, during a tracing period for contact matching, for example, the past 14 days. The smart contract on blockchain will reconstruct an ADS from the uploaded generation list, LG, and compare it with the corresponding ADS stored on the blockchain. So with the on-chain ADS, the system can establish the soundness and completeness of the generation list uploaded by the patient. Soundness means no generated identifiers in LG are tampered with and all of them satisfy the temporal conditions. Completeness means no valid generated identifier is missing regarding the tracing period. During the local cross-check, if a match is found, the client can report this case to the authority for further follow-up. A basic solution to the client's proximate verification is to use Merkle verification to prove the inclusiveness. The client will generate a Merkle path from both the patient's RG and the client's RE. Then send the matched identifier and the Merkle path to the authority for verification. However, this will undermine the client's privacy by revealing the identifier and Merkle path. So we developed a zero-knowledge proximate verification scheme to prevent the client from tampering with local contact matching results while preserving user privacy. In the zero-knowledge proof, the ADS are public, while the client's matched identifier and the encounter list LE are private. Two constraints are included in the proof. The matched ID is in the patient's generation list, and this ID is also in the client's encounter list. So the client only needs to generate and send a zero-knowledge proof PI to the authority for verification. In experiments, we first compare data storage performance by changing the number of daily confirmed cases. Our system can achieve higher efficiency for more daily confirmed cases. We further evaluate the integrity verification scheme in terms of proof size, proof generation time, and proof verification time. 4 methods are compared, and our system can conduct the verification efficiently. In this paper, we further discuss many potential research directions. For the system scalability, to enable verifiable contact tracing, the ADS and the contact data are stored on blockchain. The key challenge is how to efficiently store data for the users in the global. To solve this issue, a hierarchical chain can be first built for the ADS by increasing the tree depth and reducing the update frequency. The ADS stored in the upper chain is constructed from the ADS stored in the lower chain with a lower frequency. Second, we can explore the sharding technology to dynamically maintain regional subchains to improve scalability. Moreover, a data compression scheme and a hybrid storage model to outsource data can be studied to reduce the on-chain data size. For the data query, in the contact data verification stage, smart contract needs to query the corresponding on-chain ADS. The key issue is how to efficiently retrieve data on the blockchain. To solve this problem, a world state trie can be designed and maintained in the block to store ADS for each user. Alternatively, another idea is to design a packaging strategy to build a data-oriented blockchain by storing relevant data in the same block. In addition, in decentralized contact tracing, each user needs to conduct contact matching with a large number of patients. So to improve matching efficiency, an index can be generated for patients' uploaded records by a smart contract. For the secure computation, during the zero-knowledge proximate verification, the performance enhancement is still a problem to be addressed. Apart from using other zero-knowledge arguments, a possible direction is to encrypt the original data and outsource the verification execution to a blockchain. Alternatively, a trusted execution environment, TEE, can be used to conduct the verification on the blockchain. In such settings, novel consensus algorithms will be designed to coordinate TEE nodes and non-TEE nodes with consideration of system security. To conclude, in this paper, we propose P2B Trace, a privacy-preserving contact tracing initiative based on blockchain. A decentralized architecture is designed to record the ADS of contact records for preventing data modification. Then we propose a zero-knowledge proximate verification scheme to verify proximate claim with privacy protection. Okay, that's all. Thank you so much.